Assalamu alaikum warahmatullah. So welcome to the first lecture after the mid, and this is our lecture 10, and this is about orthogonality. Okay, so orthogonality is basically a synonym for perpendicularity. So two vectors are orthogonal if they are perpendicular. Okay, so now how to check if two vectors are orthogonal? Two vectors are orthogonal if the dot product is 0. So let's say you have two vectors v equals to some vector and w equals to some vector. So they are orthogonal if their dot product v dot w is equals to 0. So it can also be written as v transpose w equals to 0 or vw transpose equals to 0. So in case of dot product, the order doesn't matter, so that's why we can write it like this. So if we have, so how do we check if v transpose w equals to 0 or vw transpose equals to 0? So there is a small proof. So let's say you have two vectors that are perpendiculars. So let's say this is v and this is w. So if you think about this vector, the hypotenuse in this case, so this is according to the rule of addition of vectors. This is basically, okay, this is a straight line. It seems like a straight line. It doesn't seem like a straight line, but it is. Okay, assume it to be a straight line. So this is v plus w according to the rule of vector addition. Okay, now you have all studied about the Pythagoras theorem. So in Pythagoras theorem, if this is a, this is b, and this is c, we write it like a square plus b square equals to c square. So this is also true for this case. So it would be the value of w plus value of v plus value of w equals to the value of this. Okay, so you know that as these are all values, so these are basically dot products. So v dot v plus w dot w equals to v plus w dot v plus w. So this can also be written as v transpose v plus w transpose w equals to v transpose v plus, we are basically applying the rule of distribution, v dot v transpose dot w plus w transpose v plus w transpose w. Okay, so if you take these things at the left hand side, you will get this equals to 0, this addition equals to 0. So v transpose w plus w transpose v equals to 0. So this can also, as I said, that the order doesn't matter here. So these two guys are basically same. So you can write it like v transpose w equals to 0. So from it you know that v transpose w equals to 0. So you have got the proof that if two vectors are orthogonal, like in this case, then these two vectors, the dot product of these two vectors, so basically this can also be written as v dot w equals to 0. All right, so if we take a real example. Let's say you have any vector x equals to 1 2 3 and take a perpendicular vector on this. So let's take let's say 2 negative 1 0. So if you make the dot product, you'll get 0, and x plus y is equals to 3 1 3. I'm just adding these two vectors. So you'll see that the value of x is basically 14, the value of y is 5, and the value of x plus y here is 19. So you see that, sorry, there will be squares here, their dot products, their individual dot products. So you see that x square plus y square equals to x plus y whole square. Okay, so the orthogonality of the vectors are clear. Okay, so now what about the orthogonality of subspaces? Orthogonality of subspaces. So orthogonality of subspaces is two subspace being orthogonal to each other. Okay, so let's say you have two subspaces. So this is V and this is W. This is W. So let's say these are two subspaces on any vector space. So these two are orthogonal if every vector in V is orthogonal to or perpendicular to every vector in W. Okay, so V transpose W equals to 0 for all vectors V in V and W in W. Okay, so two vector subspaces V and W would be orthogonal if every vector in each subspace would be orthogonal or perpendicular to each other. Okay, so one example, you might think of one example, that the two walls of a room. Okay, so not two walls, like two walls that meet each other on a room. Let's say the floor, you have the floor and this is the perpendicular wall. Okay, so you might think that these two walls or this floor and this wall is perpendicular, but in reality this is not, because if you take one vector 45 degree on the wall and another vector, let's say like this, like 90 degree on the meeting point of them, so this angle is not necessarily 90 degree. Okay, so two walls meeting each other is not a perpendicular or orthogonal subspace. But there can be one example, that the floor of a room, let's say this is the floor of a room, and the line where two walls met. So let's say there is a line where this wall and this wall meets, let's say on this line. Okay, so these two subspaces are basically orthogonal, because if you take any vector from here, any vector if you take any vector from here, then it will be orthogonal to every vector from here. So yeah, so if you take any vectors from here, then it will be orthogonal to or perpendicular to every other vector from here. Okay, so yeah, and if you have any vector space, and if you have two, let's say this is a vector space and you have two subspaces, let's say V and W inside that vector space, then orthogonality is possible. Orthogonality is possible only when dimension of V plus dimension of W is equals to dimension of the whole space, or dimension of the actual vector space. So impossible when dimension of V plus dimension of W is greater than dimension of the actual vector space. Okay, so we'll see example of it at the last part of our class. So like one interesting fact about the four fundamental subspaces is that, so you remember about the four fundamental subspaces. So if you have any matrix A, if it is a good matrix, then in fact not a good matrix, it like for all matrix it will have four fundamental subspaces. Those are column space, null space, row space, and the left null space. So 0 is the only point where the null space meets the row space. Okay, so if you remember the picture, the big picture that I drew in the last lecture, on the four fundamental subspaces lecture, so it had a similar picture like this. So yeah, so we had, this is the column space and this is the left null space, and this is the row space, and this is the null space. So the meeting points here is this one and this one. So this so 0 is the only point. That means these points are definitely 0 where the null space meets the row space, and these actually meet each other on 90 degree. Okay, why? Because if you think about the null space and the row space, so you will see that every vector x that is in the null space is perpendicular to every row of A. Okay, as Ax equals to 0. So the null space and the row space, are basically orthogonal to each other. Let's dive deeper into this. So you have A equals to some combination of row. Okay, so let's say this is row 1, this is row 2, this is row m. This is row m. So this is a, and for ax equals to 0, what you do is you put a x here, and you want to get zeros here, m0. So how did you get the 0 here? So what you do is basically you multiply this row with this x and you get this 0, right? You multiply this row 2 and this x and you get this 0, right? You multiply the last row with this x and you get this 0, right? So this is basically row 1 into x equals to 0. This is basically row 2 into or dot product x equals to 0. This is basically row m dot x equals to 0. So as you can see that every row has a 0 dot product with x. So then like x is, so this is a whole combination of, so this is the null space, right? So this is a whole combination of vectors, and every vector from this null space is basically perpendicular to every combination of the rows, right? So the whole row space is basically orthogonal to the whole null space of A, because you take any x from the null space and you multiply every row with it and you will get all zeros at the right hand side, right? So as you can see here that like every row is basically has the relation of being 0 with the dot product of x, so that you can say that every row has a 0 dot product with every row every column entry of the null space x. So you can say that the whole row space, is basically orthogonal to the whole null space, and this is in R of n. Okay, so this is one relation, and similarly we can say that the left null space and the column space are orthogonal to each other. So the column space has a orthogonal relationship with the left null space in Rm. Okay, so one example can be given that let's say we have matrix A equals to 1 2 5 and 2 4 10. So what is the rank of this matrix? R equals to 1, because there is only one independent column here, an independent row here. So the rank of this matrix is R equals to 1. And what is the null space here? So if you put a matrix here, you will see that it is basically -2 1 0 equals to 0, all zeros. So in this case, so the dimension of this null space, so the dimension of the null space of A here is basically 2, and the dimension of A is basically the rank, which is 1, right? So in which, so the so this orthogonality works in which space? As you can see, there are 3 columns. So as you can see, the dimension of A and the dimension of n of A actually complements to dimension of the whole column space, right? Or the dimension of R3, right? So that's why I said in the previous part that the dimension of V plus dimension of W is basically dimension of the whole, or dimension of the whole vector space, right? So as you can see in this example, that the dimension of this part, which means the the matrix itself, and the dimension of the null space complements to the dimension of the whole vector space, which in this case is R3, and they work in R3. So that's why I wrote this line. That's why I wrote this line, as we are working with null space and row space. So as there is n equals to 3, so they work in R3. And if you think about the other way, like the column space and the left null space, you will see that they work in R2. Okay, so if you think about another if this had a rank of 2, then definitely the null space had to be rank of 1. In no way the rank is 2 and the dimensionality of the null space is also 2, right? Because as you can see that there are 2 rows here, so and 3 columns here. So if the rank is a full row rank, then definitely only one free column would be there, and for one free column you will get like one entry for the null space, and you will get one dimensionality of the null space. So so these numbers basically complement to each other. These numbers are complementing each other. Okay, so complementing in what sense? Complementing in this sense. So the dimension of V plus dimension of W can never be greater than the dimension of the whole space. Okay, so this can never happen to be orthogonal subspaces. Okay, so if this happens, then they are not orthogonals. So this is also true for the 4 fundamental subspaces. So the fundamental subspaces make the dimensions right. 2 orthogonal subspaces combinedly fill the whole space. Okay, so as you already know from this picture, that if the dimension is equal to the rank R, then definitely the dimension of the left null space is definitely m minus r, right? M minus r, you already know it from the previous class. So if the dimension of this one is r, the row space, then definitely the dimension of the null space is n minus r. Okay, so as you can see, they are complementing each other. So as these are in Rn, so if you add this one and this one, you'll get r plus n minus r equals to n, which is equal to the dimension of the whole vector space, and this is also true in this case. Okay, so they're basically, so that's why these vector subspaces are not only orthogonal, but they are orthogonal complements. Okay, because they are complementing each other to be equal to the dimension of the whole vector space. Okay, so so this is the main takeaway from today's class, that if two vectors or two subspaces are orthogonal to each other, then they combinedly fill up the whole vector space, or their dimensionality actually equals to the dimensionality of the whole vector space. Okay, so with this we will be starting our next topic, projection. So I have two questions which I'll be discussing in the, which, like, for these questions I'll take answers from you in the next class. So let's say you have a 3D vector space, and let's say you have any vector b, let's say b equals to 2, 3, 4. So what are the projections? So this is b equals to, okay, so this is b equals to, so what are the projections of b onto z axis and the xy plane? So let's say this is the z axis, this is x, this is y, this is y. So what are the projections? So what is this? And let's say this is the xy plane, sorry, this is the xy plane. So what is this? So there is any vector b equals 2, 3, 4, and you draw two projections from these vectors on z axis and the xy plane. So what is the measurement of these two projections? Okay, so this is the first question, and the second question is what matrices actually produce these projections onto the line and onto the plane? Okay, so what matrix should I take to make this projection from b to the z axis, and what matrix should I take to make this projection onto the xy plane? Okay, so yeah, what are the, so let's say this is p1, so p1 matrix actually create this projection, and another matrix p2 create this projection. After multiplying p1 with 2, 3, 4, we get this projection, and multiplying p2 with this matrix we get this projection. So what are these matrices p1 and p2, and what is the relationship between them? Okay, so yeah, so you see this, or if you can do it, I'll give you. So what is the relationship between p1 and p2? So if you can do it, I'll give you bonus marks for this. Okay, so thank you, and we'll see you guys in the next class, inshallah. Assalamu alaikum.